Thank you very much, and thank you very much for this opportunity to present today. My name is Shenar. I'm a postdoc at the KU Leuven, but I'll soon be moving to the University of Amsterdam. And today I would like to talk to you about a subject that is quite close to my heart, which are Wolf-Rayet stars and their production at low metallicity. But first, we've already heard quite a lot about these objects, but I don't think we yet had a clean definition. So in my opinion, there is only one definition for a Wolf-Rayet star, and that's the observer's definition. So it should look like a Wolf-Rayet star, meaning that spectrum of the object should be dominated by emission line features. And for stars, this typically imply substantial mass loss rates. And stars, massive stars, tend to launch these powerful winds necessary for the spectral appearance when they approach the Eddington limit. So when their luminosity to mass ratio increases. And in nature, indeed, this is realized in two ways. Either the mass decreases or the luminosity increases. And about 90% of the Wolf-Rayet stars that we know are thought to appear as Wolf-Rayet stars indeed because of this mass decrease because they somehow get rid of their outer layers. And they are typically understood to be helium-burning objects stripped of their outer layers, and we call them classical Wolf-Rayet stars. But about 10% of the Wolf-Rayet stars are actually thought to belong to a different category. They're still hydrogen-rich. They're thought to be on the main sequence, and these are the most massive stars we know. And because of the very high luminosities, this is why they launch their powerful winds. And in this context, first of all, these are objects that you want to study if you want to understand things like the upper mass limit or the evolution of the most massive stars. But I do want to highlight also a paper that we have just published a few weeks ago on such a massive binary, very massive binary called R144 in the R136 cluster. It is a very unique binary. It's wind eclipsing with some very interesting riddles. So do check this paper out if you're interested by these objects. But in today's talk, I want to focus on classical Wolf-Rayet stars and how we understand or don't really understand how they form. So maybe the most famous way of producing a Wolf-Rayet star is through the Conti scenario or the single star channel, where we know that basically above a certain mass threshold, we expect stars, instead of evolving towards the red, to eventually be able to strip themselves, whether it's through their stellar winds or potentially eruptions. But we don't know exactly above which masses this happens. And this has been a difficult question for quite some decades now. What is the threshold above which stars can actually strip themselves? And these thresholds I would denote with this parameter here, m single, throughout the remainder of the talk. So we don't yet have a good answer on this question, but we do think that these thresholds would depend on the metallicity. We know that as we go to lower metallicity environments, the stellar wind strength generally decreases, and therefore it would be more difficult for a star to strip itself and become a classical Wolf-Rayet star. And you can see that nicely in this illustration using BPAS tracks. And so this means that as we go to low metallicity environments, you would expect the single star channel to lose efficiency. Where exactly are the thresholds, are these metallicity dependent thresholds? Well, this is where it really becomes complicated because we simply have a lot of physical processes we still don't understand related to the progenitor's evolution, like main sequence mass loss, luminous blue variables and eruptions, cool supergiants, internal mixing, all of these things where we heard interesting talks on, and we'll keep hearing interesting talks on, affect actually these thresholds for single stars to be able to strip themselves. But what we can do is to collect different predictions that exist for from different groups and using different codes listed here. And this summary here, which is given for three metallicities, the Milky Way-like or solar-like LMC and SMC, taken from a recent paper. You can see that for the threshold masses for the Milky Way, among the different codes, the discrepancy isn't that large. But as you start going to low metallicity, the discrepancies becomes gigantic, which really reflects the uncertainties that we have to deal with at the low metallicity regime. So far, I have not mentioned at all binaries. So what about binaries? And indeed, binaries are a very important agent for stripping stars as well. So instead of becoming, say, a supergiant of some sort, if I take a star and put it in a closed binary, we have heard already quite a lot about this subject. This star is expected to get stripped either through Roche lobe overflow or a common envelope evolution. And what we get out is generally a helium star. And here, and that's a very important distinction, we distinguish between two types of objects that we may get out, a stripped star or a Wolf-Rayet star. The stripped star would appear as a Wolf-Rayet star if it is massive and luminous enough to actually launch the necessary wind to appear as a Wolf-Rayet star. And we've already heard a very nice talk by Ilva and also by Eva earlier before about these objects. I also want to highlight some of the works on these objects, including our contribution on the infamous LB1 and AJAR 6819 systems, where we actually claim that such strip stars exist. So these are very elusive objects, but it's important to remember that they're different to Wolf-Rayet stars, and you'll soon see why that's very important to remember. So we have seen that there are two main ways of stripping our stars. We have the single star channel and the binary channel. And we have also seen that the single star channel is expected to lose efficiency as we go to lower metallicities. And for this reason, it has been for a long time predicted that as we go to lower metallicity environments, we should expect to see more and more of these classical Wolf-Rayet stars in binaries. And what I want to show you in the coming slides and what we argue in the paper is that in fact, this is not trivial at all. And so first of all, empirically, and owing to several surveys by different people who are listed here, you can see that basically we do not have evidence that the binary fraction depends on metallicity or that it grows with decreasing metallicity. So you can see the typical fractions that were reported for the observed binary fractions. So it appears as if it's constant with metallicity. I do have to, however, give one big important caveat here, and that is that these fractions are generally not bias corrected. So it's a little difficult to compare them among each other, but that's something that Kaan Zilva, who is a PhD student I'm currently co-supervising at KU Leuven, is working on. So check out his recent publication and his upcoming publications on this topic. But for now, we don't have empirical evidence that the binary fraction grows with decreasing metallicity. And so why do we think that is the case? So we can divide the HRD into three domains. The uppermost domain is going to consist of massive stars that are so massive that they exceed this threshold I highlighted before. So whether they're in binaries or not, they're going to become Wolf-Rayet stars, irrespective of that. So here, binaries are actually not important in a sense in forming new Wolf-Rayet stars. Then in this window here, the stars that live here are generally not expected to be massive enough to form Wolf-Rayet stars intrinsically. But if you put them in a binary, they would become Wolf-Rayet stars. And you can see that this window is bounded by two parameters. The upper parameter is this M single we talked about before. And the lower parameter is what we call M spec, the spectroscopic mass threshold necessary for a star to appear as a Wolf-Rayet star. If a star is below this threshold and does not have this initial mass, it's not going to look like a Wolf-Rayet star after stripping, and there is ample of evidence already for this. So we see that the only place where binaries can actually contribute to the formation of Wolf-Rayet stars is in this window here, which we call the window of opportunity. And depending on the size of this window, if it's very small, then binaries will not be so important for forming Wolf-Rayet stars. If it's very big, then they would be the dominant source. So this question actually amounts to estimating the value of these two parameters. And the key point to understand is that these two parameters are metallicity dependent. The single star threshold we have already discussed, and the spectroscopic threshold simply because the winds of strip stars and Wolf-Rayet stars are by themselves metallicity dependent, in fact, very strongly so. So we can see this very clearly, and in fact, what we argue in the paper is that we can estimate very nicely the spectroscopic thresholds necessary for stars to appear as Wolf-Rayet stars after stripping. And this is thanks to the multitude of analyses that myself and colleagues have done for Wolf-Rayet stars in the Magellanic Clouds and in the Milky Way. So this is what you see here. This is the bulk of the populations, the nitrogen-rich Wolf-Rayet stars, and the red symbols are Wolf-Rayet stars that are known to have binary companions. And what I want you to note is that the Wolf-Rayet phenomenon stops below a certain luminosity threshold, and that this luminosity threshold is metallicity dependent. And in the paper, we argue, and we have good reasons to argue that these thresholds indeed approximate very well the thresholds below which strip star would not appear as Wolf-Rayet stars anymore. And you can translate these thresholds to initial masses, which is what we have done. And so for the Milky Way, we estimate roughly 18, for the LMC roughly 25, and for the SMC roughly 37 solar masses. This means that if I take a 30 solar mass star and somehow an alien comes and sucks out the outer layers and I strip the star, it would not appear as a Wolf-Rayet star in the SMC, but it would appear as a Wolf-Rayet star in the Milky Way. Another thing that I think is worth highlighting is that these luminosity thresholds appear to follow a 1/z dependence. which means that they could potentially be also extrapolated to lower metallicities with the usual danger of extrapolating results. So therefore, we do know this lower part of the window. What we don't really know is the upper part of the window, the mass necessary for a star to strip itself of its outer layers. Well, we can take the various predictions that exist that I highlighted before, which are listed here, and we can see what it means on the expected minimum Wolf-Rayet binary fraction. So how many Wolf-Rayet stars are expected to form purely through binaries? And if you do that, depending on the set of numbers that you take, depending on whatever code you choose to believe, you will find that this minimum Wolf-Rayet binary fraction either decreases with increases with decreasing metallicity or decreases with increasing metallicity, or remains roughly constant. And we don't want to argue for the validity of either of these results, but rather to show how untrivial this question actually is and why it's not clear that we should see an increase of the Wolf-Rayet binary fraction with decreasing metallicity. And so I would conclude first that the binaries do not necessarily dominate the formation of Wolf-Rayet stars at low metallicity, and we believe this is the reason. Second, it would be great if people who are doing evolution models and population syntheses mind their metallicity dependent definitions of Wolf-Rayet stars. As you have seen, it's a metallicity dependent phenomenon, and we give some helpful estimates for this in the paper. And the third point, which I haven't discussed about, is I kind of try to present a textbook knowledge of these objects, but in truth, the Wolf-Rayet populations are quite messy. They don't exactly look like what you would expect them naively to look like. So we still have a lot of problems in understanding how some of them have formed and generally their observed properties. So still some more work needs to be done in this respect.